Hi everyone. Sorry. Hi everyone. Thanks for joining the stream. Let's get started. So yesterday we were talking about Cauchy sequences, and actually we did a lot yesterday. We proved a bunch of properties of Cauchy sequences, and above else, the Cauchy convergence criteria, CCC, which says a sequence is Cauchy, a sequence of real numbers is Cauchy, if and only if it is convergent. And we also seen two interesting applications. One is proved, one is not. So first of all, decimal expansions represents real numbers. That is, decimal expansion is a Cauchy sequence, which then represents a real number. And the second is a contraction mapping principle. We only illustrated the idea of a contraction mapping principle. So a contraction is a function that satisfies the inequality absolute value of f of x minus f of y less than or equal to c times the absolute value of x minus y. So basically, the distance between the output is less than or equal to c times the distance between the input, where c is less than 1. So the distance between the outputs gets squeezed compared to the distance between the inputs. And a childhood experiment of mine is as follows. So pick a random number, pick a random real number, and you just keep pressing the cosine button on your calculator. That's my childhood experiment. And the thing is, when you spam click it, eventually the number shows on the calculator, it just settles down, okay, to a fixed value. This is because of the contraction mapping principle. So right now I'm not going to prove this, but later on when we get to metric spaces, actually I plan to alternate between Zorich and Rudin, baby Rudin. So this way you get a more, so to say, a more comprehensive coverage, I would say. Both texts have their own advantages. I wouldn't say disadvantage, but both texts are great. It's hi Ego, thank you very much for joining the stream. I wouldn't say each of these texts, Zorich and Rudin, have disadvantages, but they complement each other very well. So Zorich tends to be more, so to say, they tend to Zorich tend to provide more motivation and more applications, whereas Rudin often have deeper theorems, deeper and more comprehensive coverage of results. But I think either of them needs a good teacher, and both of them need good teachers and instructors. They can be a little bit hard for beginners, and both exercises in both of them can be hard. So it's perhaps not the best for beginners to get a more approachable experience, right? So you need simple exercises to practice the basics before you move on to more complicated manipulations. However, both of these texts, Zorich and Rudin, have difficult exercises. No, actually, a lot of people have been suggesting me various analysis textbook or just textbook in general. The thing is, I haven't read too many texts. Like my own understanding of analysis is very much heavily, so to say, influenced or shaped by two books in particular. One is Understanding Analysis by Abbott. I think that's a well-known one, right? And another is Rudin. So even Zorich is sort of new to me. I always knew this book existed, but I never sat down and until recently and seriously read it. Okay, so there's that. So our plan for today is to. But thank you very much, Al, for suggesting. Is that is that how you pronounce it? Pugh's analysis. I'll check it out. Okay. Actually, you know what? Let's just go check it out now. Pugh analysis, Pugh analysis. Okay, wow. Real mathematical analysis. What are the content list? A real number, taste of topologies. This is very similar to Rudin. Rudin also put topology, like metric topology, in the second chapter. Is there any preview here? Yeah, metric space. This is very similar to Rudin, actually. At least when it comes to initial organization. Okay, each book must have its own unique uniqueness to it. Okay, function of a real variable. Function space is multivariable calculus. Oh wow. Interesting. Where's integrals? What about derivatives and integrals? It's all in here? Oh, okay, differentiability is in here. Differentiation. Oh, hold on, what's continuity? What about continuity? So continuity is in topology? Okay. Anyway, it feels rather similar to Rudin's arrangement. Okay, so I'll take a look, but I think I'll enjoy this one. Thank you very much for suggesting the book. Okay, so today we'll continue discussing, we'll wrap up Cauchy sequence actually, and we'll start introducing the monotone sequence in the theorem. The thing is, there are two theorems that bears the name monotone, at least, okay, and it can be a little bit confusing. So in Lebesgue integration, of course, there's the monotone convergence theorem for interchanging the limit and integrals. But in elementary analysis, also the monotone convergence sequence, which we'll see, monotone convergence theorem, which we'll see today, which can be a little bit confusing. So I tend to call the monotone sequence theorem in the elementary part. I call it the monotone sequence theorem. Anyway, so this is the definition of Cauchy sequence. What about the negation of the definition? So by this definition, xn is not Cauchy. The sequence is not Cauchy if what? It is not Cauchy. So this, once again, amounts to negating quantified statement. We've already seen that example. I've seen an example of doing that for divergent sequences. Because the definition of Cauchy sequence is very similar to the one for convergence. And in fact, it can be a great source of confusion because of it. They all have this mixed quantified structure, a mixedly quantified structure, if you can call it that way. But we can just follow the general rule for negating a statement. So xn is not Cauchy if there exists epsilon greater than 0. Okay, and then for all big N, in big N, okay, there exist M and N greater than big N, okay, such that xm minus xn absolute value is greater or equal to epsilon. So there's that. You basically flip the quantifiers and then you negate the final statement. That's it. So I would just like to mention that here in the original statement, big N may depend on epsilon. You can just write exist for all big N in the negated statement, because if it's for all, then it really does not depend on epsilon anymore. So yeah, that's a negated statement. But can we give it a more verbal description? Because a statement with heavy symbols can be easy to manipulate. For example, yeah, you just need to flip all the quantifiers and negate the final inequality to get the negated statement. But just to make it more intuitive, how can we describe it verbally? Right? Because like yesterday, we also did the same. Right? So did we do that or earlier? yeah, just wanted to compare with what we did last time. Yeah, I mean, not last time, but the last time, before last time. Okay, so there you go. So divergence sequence is also have a quantified statement definition, right? That's basically the definition of divergence based on negating the definition of convergence, exactly the same as we did earlier. It looks horrendous, right? So instead of working with that, we translate that into a verbal description. And xn diverges if every real number has a neighborhood that fails to contain infinitely many terms of xn. And this is a lot easier to work with. So we want to do something similar for the Cauchy sequence too. Right? How can we translate into just plain English, but still rigorous? Okay, this way we can use it to do proofs. Oh, my goodness. All right, so there exists epsilon greater than 0. Okay, there exists epsilon greater than 0 such that how can we put this? So basically here there exists epsilon greater than 0 for all n in big N, such that for all such that there exists m and n greater than big N, xn minus xn absolute value is greater or equal to epsilon. Yeah, you just wake up and start doing math. Exactly. That's exactly what happened. Perhaps that's the reason my voice is a little bit screwed up. And yeah, so it's a great way to wake up, you know. Great motivation to wake up. Okay. So anyway, the distance between xm and xn is greater or equal to epsilon. It's a little bit hard to translate that into plain English. Guys, what do you think? How can we phrase it in normal English instead of just, well, read out the quantifiers? Is there a more concise way to, preferably notation free? Okay, that's the pinnacle of mathematical statement. Mathematical statement is the most beautiful when it has no symbols in it. So that's a personal taste, obviously. Okay, so how should we put this? So we said something yesterday about tail diameter, right? We said something about tail diameter. That could be useful because yesterday we also gave two extra equivalent definition of Cauchy sequence here. This is not actually in Zorich. The second one is from Rudin, and the third one is based on my own summary. So the second one says xn is a Cauchy sequence if it has a vanishing tail diameter. The diameter of a tail is defined as the diameter. My God. Okay, guys, let me just get some water. I'm suffering right now. Okay, give me 1 minute. Okay, I'm back. So, as I was saying, these two equivalent characterizations might be easier to work with. The diameter of a suffocation, I know, right? So, yeah, the tail diameter tends to 0 can be also used to define the Cauchy sequence proved here. So, we might just say, right? We might just say that the sequence xn has a non-vanishing tail diameter, right? Because that's the easiest way to negate the statement. So, and to do so, you can just say the tail diameter has a non-zero lower bound. If it has a non-zero lower bound, so first of all, diameter is always non-negative, right? So if it has a non-zero lower bound, it means it will never tend to zero. So that's it. There exists there exists epsilon. That's the lower bound, non-zero lower bound for the tail diameter. So that's basically the negated statement. Xn has a non-zero lower bound. Or shall we say, the tail diameter of Xn has a non-zero lower bound. And just to recall what we mean by tail diameter, meaning this is the sequence dn, which is defined as the diameter of the set xn plus 1 all the way. Okay, so that's the definition of a tail diameter, because this is the tail, the end tail, starting from xn and everything after. And where diameter of a set, okay, diameter of a set A is defined as the sup of x minus y absolute value, where x and y are in A. A is a subset of real. So that's the definition of a non-Cauchy sequence. Yeah. So based on this definition, we can do some examples. So this is example 8 in Zorich. By the way, we're doing Zorich 3.1.3a. Okay. So minus 1 to the n. Right? Show this is a Cauchy sequence. So show this is not a Cauchy sequence without invoking the Cauchy convergence criteria. We want to work with definition alone. Now, this is not Cauchy. Because the tail diameter is a constant too. Since its dn is a constant too. Right, this should be obvious. This is the picture. When x equals 1, it's minus 1, equals 2 is 1. And it just oscillates between minus 1 and 1, whatever. So the tail diameter is 2. Greater than 0. Okay, done. Next up, example 10. And this is a famous example. And we'll come back to this later. So xn is the partial sum of the harmonic series. So 1 plus 1/2 plus all the way to 1 over n. Right? This sequence famously diverges, even though intuition tells us it should converge. But yeah, intuition is wrong because it grows so slowly. There are many different ways to prove this is not convergent. But here we're just going to use the definition of a non-Cauchy sequence to prove this is non-Cauchy and hence not converge. How do you show this is not Cauchy? Well, we just need to show it has a non-vanishing tail diameter. Of course, tail diameter has a non-zero lower bound. Okay, so let's do that. And a classic way to prove it is to consider x2m minus xn. x2m minus xn, of course, are the extra terms included in x2n but not in xn. So that's 1 over n plus 1 plus all the way to 1 over 2n. And of course, each of them is greater or equal to 1 over 2n. So you just got n terms of n 1 over 2n. So 1 over 2n times n, that's 1/2. That's 1/2. So what this means is that dn is at least as great as 1/2. Therefore, dn being the supremum of xn, xn plus 1, and so on. No, not the sup, but the diameter of xn, xn plus 1, and so on, must be at least 1/2. So that's a non-zero lower bound. So we're done. Okay. Okay, so this pretty much wraps up our introduction to Cauchy sequence, and we will come back to Cauchy sequence when we discuss metric spaces, in particular complete metric spaces. Okay, so yeah, that's why I'm not proving the contraction mapping theorem stated at the end of the yesterday's stream, because essentially the proof in the metric space is identical and it's more general, so there's no need to do the same work twice. Okay, so coming back, and now let's start a new topic, which is called monotone sequence theorem. Okay, I would like to call it the monotone sequence theorem instead of the monotone convergence theorem to avoid confusion with the one in Lebesgue theory. Okay, so first of all, start with the definition. This is, from now on, this is based on Zorich. I said based on because sometimes I add my own commentary and new examples and stuff like that. Okay, for example, yesterday we broken down the proof of Cauchy criteria in the main text into several propositions. In my opinion, it made the overall flow more clear. Okay, so this is Zorich 3.1.3b. So first we have the definition that that says what is a monotone sequence. Okay, so this is rather easy. A definition: xn is increasing. Sequence xn is increasing. Of course, we all know what that means. Okay, this is interesting. It says if xn is less than xn plus 1. So I guess in Zorich, increasing means strictly increasing for all n. Okay, and xn is non-decreasing. Non-decreasing if xn is less than or equal to xn plus 1. I guess this is perhaps closer to everyday use of the term, right? If it's increasing, it should go up. It shouldn't just say, at least it doesn't go down. It's just not how we normally use the term in everyday use. Right? But seems like a lot of textbook, including the one I'm used to, consider this as increasing. Okay, just the different terminologies. Nothing substantial here. Okay, and of course we know the definition of decreasing. So xn is decreasing if xn is greater than xn plus 1 for all n in big N. Okay, so there's that. And also you have non-decreasing. If xn is greater or equal to xn plus 1 for all n in big N. Okay, so these are all called monotone sequences. Or monotonic sequences. Okay, awesome. Okay, so next up we have the second definition, boundedness, or bounded above. Right? We already defined bounded sequence in the Cauchy sequence part of the stream, namely like yesterday. So here, xn is bounded above. If there exists a number m, a real number m, such that xn in Zorich it uses less than, but I would just like to put less than or equal to because this makes proofs a little bit easier. Sometimes you don't have a strict inequality this way. You don't need to add an extra plus epsilon to make it strictly less than, you know. In Zorich it uses strictly less than, but I figured you can just use less than or equal to. There's no difference for all. And this makes proofs a little bit more, just a tiny little bit more natural. Okay, so the bounded above sequence is defined as follows. There exists an upper bound. Okay, so next up, this is the main theorem. This is actually due to Weierstrass. I didn't know that. I saw this one is rather discovered rather early. But anyway, I figured Cauchy must have knew this, but apparently it's due to Weierstrass. It says, in order for a non-decreasing sequence to have a limit, it is necessary and sufficient that it be bounded above. Oh wow, what a way to phrase it. It feels like a sentence from the 19th century, but let's just write it as if then, okay, paraphrased. I'm going to call this the monotone sequence theorem. Um, so, so if xn is non-decreasing, then xn converges if and only if it is bounded above. Okay. So this is the monotone sequence theorem, apparently due to Weierstrass. Okay, and of course the picture for that is very intuitive. So imagine an increasing or non-decreasing sequence like this. If it never goes down, so in order for it to converge, it needs to be bounded. And in fact, this is a property of the real numbers. Only if you consider xn as a sequence of real numbers, and convergence happens also in the set of real numbers, do you have this result. Okay? Because you can And you can still talk about monotone sequence in a set of rational numbers, but there's no guarantee that a rational number that is non-decreasing will converge, even when bounded above, simply because the rational number is incomplete. In fact, this is not just a convenient way to determine convergence or divergence. It's actually a fundamental property of the real numbers. You can start your theory of real numbers from monotone sequence theorem. Right? There are a bunch of equivalent characterization of the completeness axiom of real. Right? For economic purpose, for the economy of exposition, textbook typically start from the least upper bound principle. Okay? Using the least upper bound principle because that's the easiest one to state, and it does not require a lot of preliminary definition. And then use the least upper bound principle to prove a bunch of other things. But in a you can show that in a complete Archimedean field, a lot of the results are all equivalent. Monotone sequence theorem, Bolzano-Weierstrass, Cauchy's convergence criteria, nested interval lemma, these are all equivalent. You can choose any of them as an axiom and choose the rest. Okay. So anyway, so that's the picture, right? So here, this is a limit. This is a limit, but we can just show this converge by giving an upper bound. Okay, so this is the limit, the soup of the sequence. Okay. So intuitively, the limit should be the soup of the sequence as well. So this is xn, the sequence xn, and this is the soup of xn, n greater or equal to, well, 1. This should be the limit of xn. And here's an upper bound, big N. So that's the picture here. So let's try to prove it. The standard way of proving it is to use the least upper bound principle. So let's do that. No need to be super creative here. But basically, let's use the least upper bound principle. Because it's natural, right? If it's bounded above, then it has a least upper bound. You can use the least upper bound principle immediately. So it seems like a natural way to proceed. Okay, so yeah, let's complete the proof. As usual, let's start by writing assuming the conclusion, assuming the hypothesis. Assume xn is non-decreasing. And now we need to prove two direction, because it's an if and only if statement. One direction is trivial, because if xn converges, is immediately bounded, so it is bounded above. Right? So yeah, let's just put that down. If xn is convergent, we already know xn is bounded and thus bounded above. That's it. Okay. So the key really is the converse. Right. So now assume xn is bounded above, and need to show xn is convergent. need to show xn converges. All right. So to show xn converges, we have to propose a limit, or you could use Cauchy criteria. But here, because of we already assumed it is bounded above, there exists a least upper bound, and based on this picture, this obviously should be the limit. So we have a proposed limit. So let's do that. Okay, so by the assumption by LUBP, least upper bound principle, the set S, which is S, which is defined as the sup of xn, n greater or equal to 1, exists. Okay, so that's the first sentence, and we want to claim that S is the limit of xn. Okay. Okay. So then, and indeed, this is the case. You can use the definition of sup. Think about it. Let's see what can we do to prove this claim. Let's start by let epsilon greater than 0. Proof of claim. Let epsilon greater than 0. Okay, what do we need? We want to show there exists big N such that for all little n greater than big N, okay, xn minus s absolute value is less than epsilon. Okay, so can we draw the situation on the graph here? So this is S, and xn and s has distance less than epsilon. So let's draw an epsilon tunnel. This is s plus epsilon. Okay, and this is s minus epsilon. So we want to show that xn eventually completely falls into this gap. So how do we show the big N exists? Well, the thing is, s minus epsilon is all that matters. You see, s plus epsilon, this part of the gap is empty. There's no dot in here. We don't even need to bother with this part, because it's already the sup, right? It's already the sup, so it's an upper bound. So every xn is already less than or equal to s. So you just need to worry about the lower half. So that means we only want a big N so that when little n is greater than big N, x little n is greater. So you only need xn is greater than s plus epsilon. That's all we care about, because of the monotonicity. Oh no, actually not monotonicity, but the boundedness. It's due to the boundedness. But this is obvious because s minus epsilon is not an upper bound. S is the least upper bound. So yeah, s minus epsilon is not an upper bound. If it's not an upper bound, there's got to be an element that is greater than it. So you're done. So let's write it formally. Okay, so let epsilon be greater than 0. So then s minus epsilon is not an upper bound of the set xn such that n greater or equal to 1. Okay, it's not an upper bound of this set, and hence there exists a big N in the set of natural numbers such that x big N, okay, x big N is greater than s minus epsilon. Okay, and now you can use the monotone assumption. So suppose little n is greater than big N. Okay, since xn is non-decreasing, the sequence is non-decreasing, we have xn is greater or equal to x big N. X big N. So therefore, overall, you have the following. That is, xn is greater or equal to x big N, but x big N is greater than s minus epsilon. As the picture shows, here you see this is a big N. And now, on the other end, right, this is the trivial upper bound. xn is less than or equal to s, which is less than s plus epsilon. And as a result, xn minus s absolute value is less than epsilon. So now we have all the ingredients in the definition of convergence. For an arbitrary epsilon greater than 0, there exists big N such that for all little n greater than big N, xn minus s absolute value is less than epsilon. These are all the ingredients needed in the definition for convergence, and hence you can say, therefore, by definition, of limit s equals the limit of xn as claimed. And this completes the proof. So yeah, that's it. All right, so that's the monotone sequence theorem, right? This is probably all the textbook, Russian or non-Russian, uses this method to prove the monotone sequence lemma, unless this is taken as an axiom, of course, and then you will have to you either for an axiom you just assume it, or you may prove it using a construction, a model for the real numbers, such as the Dedekind's cut or Cantor's construction, that is equivalent classes of rational Cauchy sequences. So this is typically how it's done in real analysis. If the monotone sequence theorem is treated as a theorem, okay, if it is treated as a theorem, not an axiom, you usually prove it from the least upper bound principle. Okay. So of course, this theorem here, the proof of the theorem says more, right? The limit is the supremum. Right, so remark, from the proof, we actually have xn non-decreasing implies that the limit of xn is a supremum. Not just convergence, you can say something about the limit. Unlike in the Cauchy criteria, you can say nothing. Right? In the Cauchy criteria, because the sequence aren't necessarily monotone, so you just know it converges, you don't know what the limit, you can't even describe the limit. Right? It just exists. Okay, so limit of xn is the supremum of xn, n greater or equal to 1. Okay, and analogously, a completely parallel situation, not analogously, but rather similarly. Similarly is a term that we use to indicate the proof is entirely the same, not just an analogy. So by changing the direction of inequality, you can just get similarly xn non-increasing implies that the limit of xn is the infimum. The limit of xn is the infimum of xn such that n is less than or equal to 1. That's it, right? That's the extra information we get from the proof. Okay. So anyway, now let's come back to, let's do some more examples, shall we? Yeah, let's do some examples, and some of the examples will be quite useful not just as examples, but but actually results of interest on their own. So this is example 11. It says the limit of n over q to the n as n tends to infinity is 0. If q is greater than 1. Let's see how it's done. Okay. So, and here's the proof. It goes like this. Let's write xn to be the sequence n over q to the n. Okay, so we want to investigate the monotonicity, right? After all, this chapter, a section on monotone sequences. So you want to see the overall trend. The intuition is that q to the n grows faster than n eventually. Right? So if q is barely greater than 1, initially the exponential function may start out slow, but eventually will surpass the linear growth. This is how you make money. Right? This is how you make money. This says what? Okay. This says what? It says if you only have salary, then it's not good. If you only have salary, then no compound interest going on, and eventually you will be left in the dust. Right? Because compound interest grows under compound interest, theoretically speaking, wealth grows exponentially. Even when the accumulation factor Q might be small. Let's say even when the interest rate is very small. I mean, real interest rate, okay, doesn't count, already taken inflation into account. So yeah, start saving early, this theorem tells you. Because linear growth represents your salary. So assume constant salary, of course. And you might have a big salary, but it's constant. And q to the n, even when q is very small, it's barely greater than 1, very low interest rate, eventually compound interest wins out. Right? So that's basically the interpretation, a real life interpretation of this result. So and that helps us to get an idea of the behavior of the sequence. Eventually it should go down, right? N over q to the n, eventually it is decreasing. I said eventually because initially n might still grow faster. So let's see how do we prove this. Okay, because this is a ratio, so we might consider just taking xn plus 1 over xn to see what happens. Right? If this is, say, so we want to show, the idea is, as we said, q to the n eventually grows faster. Than the linear term, n. So eventually grows faster, that means q to the n, so xn will be eventually decreasing. Xn eventually decreasing, that means eventually xn will be less than or equal to xn plus 1. Right? So this is all we need. Okay, so that just means equivalently, if you take the ratio, that means xn plus 1 over xn is greater or equal to 1. Right, so that's the idea. No, less than or equal to 1. What am I talking about? Decreasing. Okay, xn is greater or equal to xn plus 1. Oh, it's my cat. All right, xn plus 1 over xn, this should be eventually less than or equal to 1. So that's what we're going for. That's our goal. So let's just calculate the ratio. All right, so xn plus 1 is n plus 1 over q to the n plus 1 over xn, which is n times n over q. And this simplifies to m plus 1 over n, and then times q. Yeah. So the temptation is to take the limit, and indeed we can. This converges to just 1 over q as n tends to infinity, which is less than 1. Which is less than 1. So what can we say about this? Because we have a result regarding limit and inequality sometime earlier, here in August 11th, 2 days ago, we proved this property here. Passage to limit and inequalities. Here, there's a result. So yeah, if suppose xn converges to a and yn converges to b, if a is less than b, okay, then there exists, then basically xn eventually less than yn. So this is the theorem. Okay, let's just paraphrase that and see how this, I mean not paraphrase, just copy it here to see how this can be applied. Okay, this is from 3.1.2, Zorich. Okay, and here we can just treat yn to be constant. Let yn to be a constant sequence 1. So yeah, and xn here to be the ratio, xn plus 1 over xn. So the idea is eventually xn will be less than yn. That means eventually xn plus 1 over xn, here this sequence will be eventually less than 1. Okay, so therefore can say xn plus 1 over xn is less than 1, or should we say for all eventually. Eventually, i.e., there exists a big N in a set of natural numbers such that for all little n greater than big N, xn plus 1 over xn, this is less than 1. Is less than 1, or yeah, so basically that's it, right? So or can say xn plus 1 less than xn eventually, or xn decreasing eventually. Because all it matters is that it's the ultimate behavior. Only the ultimate behavior, the eventual behavior, matters when it comes to limit. Okay, so yeah, then you can just apply the monotone sequence theorem, or actually you also need boundedness. Right? We also need boundedness. We just need bounded below. Right here in the original sequence, monotone sequence theorem is non-decreasing. Here we have non-increasing, or in fact we actually do have strictly decreasing sequence, strictly ultimately decreasing. So we just need to show it is bounded below, and this is obvious. And obviously 0 is a lower bound. So xn is also bounded below. Indeed, xn is positive for all n. Okay, so now you can combine those two, decreasing eventually and bounded below. And so say by therefore by the monotone sequence theorem, xn has a limit. The limit of xn exists. Okay, so now we just need to show it is 0. How do you show that is 0 then? Well, let's just call the limit, say, call it x. Say x, shall we? We have this relation earlier. We have this recurrence relation, if you will, xn plus 1 over xn. Right? You can use that to our advantage. So therefore, x is the limit of xn, which is the limit of xn plus 1 as well. But xn plus 1 is xn times n plus 1 over n times q. And now you can use the product rule, the product law for limit. xn converges to x, and n plus 1 over n converges to 1. So this is just the limit of xn, here, use the product law, limit of xn times the limit of n plus 1 over n times q, which is x times q. So you get an equation for x. Oh, here, q should be at the bottom, my bad. Q should be here, Q should be here, so this is just x over q. You have an equation, therefore x is x over q, and the only solution is 0. That's it. So x is 0, and so overall, the limit of n over q to the n is 0, and we're done. Okay, so that's a nice example. Next up, let's do another example. So I think in regular calculus, you typically prove this using L'Hopital's rule. You treat n as a continuous variable, say x, and then you differentiate top and bottom, which is a little bit of overkill, right? Here we're only using the most basic results in analysis, but typically in calculus, this sort of reasoning is perhaps in a bit more advanced than typical calculus sequences. Anyway, so here let's continue with the next example / corollary. This is called a corollary in Zorich. So I suppose it should follow from the previous result or examples rather quickly. So this is a very useful result. It says the limit of the nth root of n is 1. Yeah, this will be used quite often in, for example, the root test. The root test in series. So eventually, I think not too far actually. Yeah, so in Zorich, the series is in It's in the same chapter. Great, awesome. So we'll be dealing with series very soon. Yay. And this corollary will be useful there for various convergence tests for series. So now let's take a look at how this, as a corollary, how does this work? Well, let's consider the idea. We need what? So first of all, the n is greater or equal to 1. So the nth root is always greater or equal to 1. So you have a lower bound. This is a lower bound. 1 is a lower bound for the sequence. Right? That's a lower bound of the sequence. And now we need to show it is decreasing. Or does it have to be that complicated though? It doesn't have to be that complicated. You just need to say n is greater or equal to 1 is less than 1 plus epsilon over 1 plus epsilon to the n, and you just take the nth root. I suppose you can take the nth root, right? I mean, I'm saying this, of course, algebraically this is valid. I'm just saying this is nth root defined in the book. It must have been, because it's like this. Because I don't want to use any circular reasoning or any kind of operation that has not yet been defined. Because I didn't start the book from the very beginning. Because earlier, remember there was a day that I got stuck with a silly problem because I refused to use log, because log was not introduced, okay? Log is still not introduced in this part of the book. So here I just don't want to use things that aren't yet defined, but seems like because if you're already using the nth root, this should be okay, okay? So I'm now just going to use the property of the nth root. That's what I'm trying to say. I'm just going to use the property of the nth root and then take the nth root on both sides, just greater or equal to 1 less than 1 plus epsilon. And this is of course just the same as nth root of n minus 1, absolute value less than epsilon, and we're done. You see, this just uses definition. There's no need for using a monotone limits theorem or whatever. So that's it. So this is not really a corollary. I don't know why it's called a corollary. Weird choice. Because if it's a corollary, it suggests it follows from the previous example or the previous theorem, right? This just follows from the definition of convergence. I don't know why it's called a corollary. So let's do that. Okay, so this is just an application of the definition. So let epsilon greater than 0, just finish that off real quick. And actually, is this always true then? Oh no, it's actually it is. It is a corollary. It is a corollary. What am I talking about? It is a corollary. Okay, so it is a corollary not of. It is a corollary of the. Hang on. Let me try to pin down the exact application, because this kind of looks like the proof. Kind of looks like the proof. We said okay. So this inequality is a linear term eventually gets beaten by exponential, which is exactly what we just proved here earlier. So this is indeed a corollary. Okay, I'm using it without realizing I was using it. Okay, my bad. So let epsilon greater than 0. So by the proof, oh hi, hi Vernon, hi everyone for joining the stream. Thank you very much. So by the proof of the previous example, we have n over 1 plus epsilon raised to the n less than 1 eventually. Okay, that's it. Okay, so i.e. there exists a big N index such that for all n greater than big N, little n over 1 plus epsilon raised to the n is less than 1. Okay, and then we can use what we have here. Okay, so now suppose n is greater than big N, then n is greater than 1, greater or equal to 1, less than 1 plus epsilon raised to the n, and then we take the nth root. Assume that the monotonicity of the nth root function is already known, okay? So it's just 1 on the left-hand side, and this will imply the square root of n, no, the square nth root of n minus 1 absolute value is less than epsilon. So now we have all the ingredient we need. Arbitrary epsilon greater than 0, there exists big N, suppose little n greater than big N, and finally distance less than epsilon. Okay, so yeah, that's the end of the proof. Okay, I should, formally speaking, write a concluding sentence, but I'll just skip that now. Okay, because usually when it comes to writing a concluding sentence, typically if the proof is very long, it's perhaps it's just tiresome to read the whole thing, and you might actually get the result without letting the reader knowing about it. But this is very short, so I don't think there's any confusion going on. Okay, but there should be okay, a concluding sentence. As a beginner, you should always do that. Okay, do what I say, not what I do. Right. Corollary 2. Corollary 2. Okay, let's go to the next example. Here it says it also has to do with the nth root. So the limit of the nth root of a is 1 for any a greater than 0 actually, not 1. Okay. So what do we have here? I think it's similar, right? So here you have the exponential eventually beats the linear function. And of course, exponential will eventually beat the constant function too. So basically, this is our scratch work. Okay. So yeah, we want the nth root of a minus 1 to be less than epsilon. Okay, so the nth root of a minus 1 less than epsilon greater than minus epsilon. The nth root of a the nth root of a this is greater than 1 minus epsilon less than 1 plus epsilon. Okay, well, maybe we can consider, say, a is greater than 1. Let's consider a to be greater than 1. Then the nth root will always be greater than 1, so the left-hand side is trivial. So if a is greater than 1, then if a is greater than 1, then you already have the nth root of a greater than 1. So the left inequality is trivial. say greater or equal to 1. Okay, and here on the right you have 1 plus c epsilon. And take the nth power on both sides, you get a is greater or equal to 1 less than 1 plus epsilon to the n. And this is obviously true. Exponential function do eventually be constant, right, for any a. Right, so it is unbounded above. What we actually prove it. This is the one I struggled actually here in the lemma. No, not this one, but the one on the Sunday. I was struggling with this one, the lemma. It says exponential function eventually beats any constant. Right? And I wrote a follow-up post to correct my confusion. Okay, so now we can use it. So here. So yeah, this is what we have. This is what we have in our Scratch work. So let's just start by writing up the case a greater or equal to 1. Proof. So let epsilon greater than 0, we always need that. We consider two cases of a. For a. So for a, okay, so one is case a greater or equal to 1. Basically what we have here. So then there exists big N such that there exists big N such that for all n greater than big N, a is less than 1 plus epsilon to the n. And this is by the lemma. By the lemma from, let's quote that. So this was the lemma that I struggled with, and now it's fixed. So going back, let me try to find the exact number of it. Yeah, so that's the lemma on page 62. And it's from section, hang on. Okay, and here's from section 2.2.4, part C. 2.2.4 part C, okay? So that's it. Right, so that's the result we're using. Eventually, the exponential function beats an arbitrary constant. Okay, so that's nice. And now we just reverse the logic we did in the Scratch work. So now suppose we need all the ingredients in the limit definition. We have let epsilon greater than 0, we have there exists big N, so we need suppose little n greater than big N. Then just reverse the logic. Then 1 is less than equal to a, yeah, less than 1 plus epsilon raised to the n. Take the nth root, you get the nth root of a is greater or equal to 1, less than 1 plus epsilon, and then which implies the nth root of a minus 1 absolute value is less than epsilon. Okay, so this is what we need. In this case, therefore, the limit of the nth root of a is 1. So this is the first case. Now let's consider the second case. The second case is where you have a is greater than 0, less than 1. So actually now we don't need to start from scratch and redo the epsilon big N argument, because you can just consider the reciprocal. And here 1 over a is greater than 1. So by the previous case, you can apply the previous case for 1 over a. The limit of 1 over the limit of the nth root of 1 over a is 1. So basically, now you can use a limit law and the rule for the nth root. So therefore, 1 equals the limit of 1 over the nth root of a, okay, which is 1 over the limit of the nth root of a. And as a result, the limit of the nth root of a is 1 as well. So in both cases, combine two cases overall, for all a greater than 0, limit of the nth root of a is 1. So we're done. So that's another corollary. Actually, this isn't a corollary, I was thinking. This isn't a corollary based on the example, huh? Based on this example? Or is that a corollary of corollary 1? Where did we use corollary 1? We didn't. We didn't use corollary 1. We just prove it from the definition. So questionable whether it's considered a corollary. Or is that how it's done in the book? It's based on corollary 1? I don't know. Let's check the textbook's exposition. It really didn't say, so I don't know. Like, it's fine. We proved the result. We can move on now. Okay, so once again, don't just move on. Okay, don't just move on and just when we do math, when we think about, we need to think about whether a result is worth like remembering, or it's just something that we just prove it and brush aside. And I think those two will both prove to be very useful later. Okay, because as I said, in the series convergence test, we will be seeing something called this root test, useful in root test. Okay, so worth remembering. All right, so next up we have example 12. Next up is an example. This is also super useful, actually. It's useful for the exponential theory, exponential series. Okay, example 12, also very useful result. So it says the limit of q to the n over n factorial is 0 for any q. So now we have a hierarchy here. Right? Example 11 says eventually exponential function beats linear function. But here you have another even more powerful function. The factorial eventually beats the exponential. This is what it says. Okay, so let's prove that. So why don't we consider the same strategy we did for example 11? Because generally speaking, when you have a bunch of exponentials and factorials, taking ratio is a good idea. Right? Remember how we completed example 11. The idea is the bottom eventually grows faster than top, so you consider taking the ratio to show that the sequence decreases eventually. Right? So let's do that. The same idea. Okay? The idea is factorial eventually, quote unquote, beats exponential. So let's do that. Proof. Let xn be q to the n over n factorial. Okay, let's write q x of xn, right, be this sequence. So now we can write, let's calculate xn plus 1 over xn. All right, so this just gives us q to the m plus 1 over q plus 1, oh no, m plus 1 factorial. It's kind of like ratio test, right? In calculus, kind of like ratio test for series in calculus. Q to the n over n factorial. So now you have q over m plus 1. That's the result of the algebra. And obviously this will tend to 0 as n tends to infinity. And this is true for all q. Oh, sorry, yeah, this is true for all q. So you have that. But the thing is, we don't know whether this is increasing or decreasing. We don't know that. So actually, why don't we consider the absolute value of this term? Right? Why don't we consider the absolute value? This way, you can use the monotone limit theorem. Right, taking the absolute value, shall we? Yeah, let's take the absolute value so that the ratio is q over is, yeah, so this way the ratio sequence is decreasing. Actually, we don't need the ratio sequence decreasing. We need what? We need to show, okay, what we want here. We want xn plus 1 over xn to be less than 1 eventually. But it's 0. Okay, so, wow. So it is less than 1. You just need it to be less than 1. Here you actually have it much better. So this is less than 1. Okay, cool. So yeah, you can just say this eventually is less than 1. This ratio is eventually less than 1. And we work from there. So therefore, there exists big N as an index such that for all n greater than big N, the ratio xn plus 1 over xn is less than 1. Right, so this is eventually decreasing, i.e. xn as a sequence eventually decreasing. And obviously xn is bounded below. Since xn is greater than 0 for all n. And therefore, by the monotone sequence theorem, okay, the limit of xn, say, equals x, okay, as x, which is, say, defined as the limit of xn exists. Okay, so you now have the result that limit exists. Let's move on. Just use the same trick. Okay, you have the limit of xn plus 1 also equals x. So that's the limit of xn times the limit of xn times q absolute value over m plus 1. Okay, use the limit law. That's the limit of xn times the limit of q absolute value over m plus 1. Oh, but that's just 0. It's just x times 0, so it's just 0. There's not any need to solve an equation. So that's it. Okay, so x is 0, so therefore overall we conclude, therefore the limit of q, the limit of xn is 0, and this implies that without the absolute value, the inner term also tends to 0. The limit of q to the n over n factorial is also 0. Okay, so we're done. And of course, this is useful for the exponential series. This is a general term in the exponential series. Hi, JC. Wow, thank you so much for joining the stream. Good to see you here. Awesome. Thank you very much. Okay. So these are awesome examples, and we still have tons of time left, actually. This goes way better than I expected. Cauchy sequences are fun, I know, right? Yeah. Cauchy sequences are immensely useful in practice also, because let's say you design an algorithm, an approximation algorithm, in numerical analysis, and you don't know a priori whether the sequence converge. So you first try to show it is Cauchy. Right. Yeah, JC practice math, guys. Go check out JC's stuff if you haven't done so already. He streams regularly, and he has a series on his main channel. Math Can Be a Hobby. I'll just put the link here. So he has 2 channels. Okay, so recently he changed. He started a new live stream channel. JC practice math is. Now he does his live stream. Another main channel called Math Can Be a Hobby is where he posts his videos and stuff. Yeah, JC, because I should do more like numerical analysis, because numerical analysis tend to have this stereotype of being an engineering tool, right? You just plug and chug. But really, numerical analysis is also a branch of analysis proper. Like you do the same kind of proofs, epsilon, and over there, epsilon actually takes on a specific meaning. That's the machine accuracy there, right? So numerical analysis becomes just a parallel, or actually a subfield of analysis. You use the things like Cauchy sequences, monotone convergence, that sort of thing over there as well. But instead of just declaring n exists, you actually need to construct, okay, how do you prove the order or the rate of convergence? The rate of convergence matter. Yeah, it was very fun. Yeah, definitely. Numerical analysis it started off as a branch of computer science, but right now it's kind of moving away from computer science now. It's kind of a standalone subject. Because, of course, numerical analysis is where computers were first invented for, right? To do those tedious calculations, repeat those tedious calculations, but very fast. But then again, computer science has its own unique problems, and numerical analysis and becomes bigger and bigger as well. So kind of part of the way, yeah. So, but definitely there are still cousin disciplines. So anyway, here, guys, JC practice math, and that's his new channel. For live streams, mostly. He could, of course, publish videos there, but right now it seems to be mostly live streams. And math can be a hobby. Right. So, and he has a proof series. A math can be a hobby. I'll just put the link there, his main series. Based on Serge Lang's book. Hang on, where's the share link? Okay, anyway, I'll just put the channel here. You can find the series very easily on the main channel. Yeah, so he starts from basic mathematics without any bias towards specific field, right? So right now, what I'm doing is part of the bridge course. I'm trying to design for the measure series, because measure theory really needs your background in analysis, or more specifically, you need proof writing skill, manipulating quantifiers, manipulating sets, that kind of thing. even when the specific proofs of measure theory don't rely on, say, a result in real analysis, but the flow is so similar that if you don't have experience working with, say, more concrete examples like actual sequences, doing proofs in measure theory without prior experience in analysis is very hard. So this is what series is about, okay? To help people to get into more advanced text without proof background as soon as possible. Right. So let's say I'm just having, like when I started the channel, I have a target audience in mind. I mean, perhaps not when I started, but like definitely a year ago or so. I was saying, well, this is an applied math channel, so probably a lot of people from non-math majors would be interested in that sort of thing, from physics, from engineering, social science, that need math but haven't taken formal proof course in math, might be interested in applied math. So like picture someone who has already taken, calculus, linear algebra, but mostly just calculations, but now they wanted to enter more advanced stuff like, I don't know, like control theory, partial differential equations, or statistics and machine learning, and they need to read textbooks, which of course involve some kind of proof, and they will struggle because they don't have prior experience of it. So what do we do? Right? So this course is specifically designed to solve that issue and not particularly aimed towards developing just say an overall, like from the ground up, okay, just like a bridge course. That's really what is it about. But JC, he does things very comprehensively. He actually started from the integers, addition, like induction, that kind of thing, and which are universal skills. And because the concept's already clear from the user, you know how to do addition, obviously, but to prove things from the ground up isn't always easy. And it's not just it's not a bureaucratic exercise. This is how actual mathematicians work. So yeah, definitely go check out his intro to proof. It's different emphasis. So no worries. Like you see, like I want to do algebra myself, but I just don't have time. It's kind of a shame. I should definitely, when I kind of wrap up what I'm doing now, like there are some loose ends currently, and so I can spend some time on the algebra. Yeah. Yeah, exactly, right? So, yeah, I think like your target audience is perhaps much more prevalent online. Hating math is kind of socially acceptable, let's be honest, but yeah, but it's awesome. So, have you tried a lot of AI and ML aspirant? I think this kind of math is becoming so much more valuable. Yeah, yeah. So I think a lot of my audience are tuned into the channel because of the stat stuff initially that got my channel to a little bit of attention because of the statistics stuff I'm doing. Right now, I haven't posted much statistics videos in a while. The latest one is about, well, which one though? I can't even remember what's the latest statistic video I post, but I should really post one. It's been working, like stuck in the dev hell for ages. It's called Why the Sample is an IID. Okay, so when is a sample IID? So that was my video, and it got stuck in the dev hell, and I really hope to publish it perhaps next week. Yeah, next week definitely. Okay. Anyway, so now let's take a look at a very special number. Very special number, the number E. The number E. Okay. So how is the number E defined? I say, nice. Stats used to be top of my mind for subject after linear algebra. So much traffic now for probability and LA. Yeah, exactly. Exactly. Statistics. There's a lot of videos on YouTube about, more practical statistics, like how do you say execute a t-test, right? How do you plug in the numbers and use the packages, do the visuals, that kind of thing. Of course, these are, of course, very valuable skill, but I think there's a market. There's a market for the foundations of statistics. Show me the math. Like, how does this black box of a t-test work? Right? What are the assumptions in there? I think more and more people are having, so to say, this kind of appetite, right, for rigorous statistics. So I figured, why don't we start to do that, right? And well, it turns out to be quite successful, if I do say so myself, because it went way beyond my expectation. Yeah. Awesome. Awesome. Thanks a lot, dude. So now we're going to define the number e. So the number e can be defined in various ways, right? Let's just put a few on the side. So if you have some experience with calculus, of course, e is 2.71828 and so on, right? I think high school knows this, right? High school already introduced this number e. And there's several ways, at least three on top of my mind, that you can define e. So e can be a limit of a sequence, limit of 1 plus 1 over n raised to the n. Right? And what else? It can be a series. It can be a series of the summation, 1 over n factorial, n goes from 0 to infinity. It's also a popular definition. I think in Rudin, E is defined this way. This is the definition of E in Rudin. And you can also define E using derivative. And that's the definition of E in Stewart. So Stewart's calculus defines E this way. So consider a general exponential function, f of x equals a to the x. We know from calculus that the derivative of f of x is a to the x times the natural log of a. So exponential function has this property that its derivative is a multiple of itself. Stewart defined E as the number a such that the derivative of f, the derivative of a to the x equals a to the x, such that a to the x prime equals a to the x. So that's also a definition. It's quite interesting. Here we're taking this as our definition. We're taking this, what I call the compound interest definition, because it's related to compound interest. Okay, so before we prove this, okay, let's just see why this is connected to compound interest. So here, the idea is, because this, I think it was due to Bernoulli, one of the Bernoullis for studying compound interest. So let's say this is your time period, say 1 year, just one period, okay, 0 to 1 period. You can think of period as a year or 10 years, don't matter. It's a fixed amount of time. And let's say if you deposit $1 at the start, okay, and the interest rate for that period is R. The interest rate is R. Interest rate is R. So if there's no compounding, if it's simple interest, then at the end of the period, you just get exactly are extra dollars. So number of compounding, let's make a table. That's the first column, and the second column is the accumulation value, accumulated wealth. I think I saw a video about discovering E via log table calculation. Oh wow, log table. That's old. I think that's equivalent to Stewart's definition, but thought it was really interesting perspective. I see. Awesome. So the accumulated value is as such. If there's zero compounding, then you just get 1 plus r at the end. That's the definition of interest rate after all. So if, let's say if you, actually this is compounding once. That's like, think of it as compounding once. Okay. And actually number of period of compounding, let's just put it this way, period of compounding. So in this first case, it's called the simple interest situation, simple interest, which is not really compound interest. So compound interest happen when you have at least 2 periods of compounding. So there's this rule, okay, it's a purely artificial rule, that if you have 2 periods, then the interest rate, individual interest rate for each period is going to be the original interest rate R over 2. So R over 2, half R here as the interest rate for the first period and the same for the second. Why? I don't know. Perhaps people was too sick and tired of calculating the rules and stuff. They just decided, okay, this is our rule. This is our policy. Okay? So divide the nominal interest rate by the number of periods throughout the entire duration. That will be the effective interest rate in each period. So in this situation, after the first half, after the first period of compounding, you get 1 plus half R. That's your total wealth. And then you put the total amount, the new principal. You deposit the new principal. Okay, you're not going to extract the interest. You're just going to deposit the new principal, and because every time you redeposit, right? After that period, it gets multiplied by a factor of 1 plus half R. So at the end, you get 1 plus half R squared. You can see where this is going. So in general, if we have n periods of compounding, you get 1 plus R over n raised to the end. So that's the formula for compound interest. And let's see what happens if you increase the number of periods. For example, for n equals 2, let's expand the expression and see how does that compare to simple interest. The idea is, because here in the middle you increase the principal, right? So the interest should also increase by a little bit. And let's see whether that's true. So expanding this, you get 1 plus R squared over 4. So indeed this is greater than 1 plus R, as our intuition suggests, because you increase the principal in the middle of the period. So it makes sense that 1 plus R over n, right, 1 plus R over n raised to the n is increasing intuitively. Because in this process, you keep increase the principal throughout the period. This is intuitive, but it still hasn't yet proved. Because it's not obvious, right? The base is decreasing. 1 plus r over n, the base is decreasing, but the exponent is increasing. So there are two competing factors working against each other. But the net result intuitively should be increasing, as we're increasing the principal throughout the entire period. So the natural question is, what happens when n tends to infinity? Does this, for example, it would be great if this sequence increased without bound. Then we can just sit at home all day and stop working, right? You can just let the compounding do its magic. Of course, compounding is important, but not that powerful. Okay, as it turns out that if n tends to infinity, this sequence 1 plus r over n raised to the n will converge to a constant. Now that constant is e to the r. Right, so that's the idea, what we're going for. So now let's just take a look at the special case where r is 1. Okay, r is 1, and we are going to actually prove this sequence converges, and the limit is called e. Okay, so that's the intuition. And let's start with the definition. So this is example 13 in Zorich. So the idea is we're going to prove the limit of a 1 plus 1 over n raised to the n exists. And after that, it will be called e. Okay, and after that, you get a definition called e is defined as the limit of 1 plus 1 over n raised to the n. So that's our definition. But you first need to show the limit actually exists, because otherwise the definition is meaningless, right? Okay. To do so, we're going to need a lemma called the Bernoulli's inequality. Now, Bernoulli's inequality is something we actually showed already in one of our previous live streams, but let's just do that again for completeness sake. And it's not that long. So the Bernoulli inequality is our key ingredient, the lemma. There's so many Bernoullis, it's impossible to know which one discovered the inequality. And there's also, if you guys don't know, there's intense sibling and also generational rivalries in the family about who discovered what, and it was petty. Anyway, there's also, I believe, father plagiarized the son, which is kind of dramatic, but go look up the Bernoulli's family. Very interesting. So Bernoulli's inequality says for all n and for all alpha greater than -1, we have 1 plus alpha raised to the n is greater or equal to 1 plus n alpha. Okay, so if you know calculus, then this can be easily interpreted. Okay, so the geometric intuition is as follows. So let's consider the function f of x, okay, f of alpha. Okay, let's consider the function f of alpha equals 1 plus alpha raised to the n. Of course, it will have a 0 at -1. Yeah, there's a lot of Bernoullis actually. Guys, there's a lot of Bernoullis. There you go, Bernoulli family. They have their family emblem, I believe, Bernoulli family. It's a powerful family from Switzerland, and I believe they still exist. The Bernoulli family, they still exist. You see, these are the members: Jacob, Johann, Nicholas 1, Nicholas 2, Daniel, Johann 2, Johann 3, Jacob 2. And these are Many of them are, I think, yeah, there's just too many contributions from the Bernoulli family. And for example, in probability, we use the Bernoulli distribution all the time, and I don't even know which one invented it. The Bernoulli distribution 0 or 1, Bernoulli trials. Yeah, this is perhaps the single biggest family of mathematicians in history in terms of the quality of their work and the number of individuals. And nowadays, people can barely tell these fellows from each other. But yeah, this is a family tree. Go check this out. It's so interesting. And there's also family rivalry, or Bernoulli family rivalry, mass drama. Bernoulli family rivalry was a fierce multi-generational feud among a Swiss dynasty of mathematical geniuses. Brothers Jacob and Johann, later Johann and his son Daniel, competed bitterly through public insults, plagiarism, and sabotaging each other's careers. It's very dramatic. And nowadays, ironically, nobody can tell them apart unless you study the history of math very seriously. So, this kind of things always makes me come to like one of the recurring theme of the channel is that do not worship scientists. Okay, of course we honor their labor, that's 100%, but they're human beings. They're fallible people as well. Like the one I keep mentioning is Gauss's rivalry with Legendre over not just the method of least squares, but was also, I think, the results in number theory as well. Yeah, and Gauss was very, was very hungry for fame. He wanted to keep his reputation as the prince of mathematics. So he refused to support a young Hungarian mathematician called Bolyai, I believe. I might have mispronounced his name, but basically Bolyai also discovered the non-Euclidean geometry. He asked for Gauss's opinion, but Gauss was afraid that this is too philosophically controversial, and even though he himself also discovered the same idea, he refused to publish it and refused to support that young fellow mathematician, so which broke his heart. These people, they're smart, they're hardworking for sure, and their achievements are genuine, but that does not save their soul. Okay, so anyway, that's a side tangent, but this is a very interesting piece of math history, the Bernoulli family. Here, for example, I have no idea who invented the Bernoulli's inequality. Okay, anyway, so coming back to yeah, I'm an algebraically leaning guy, so I don't know that family as well. Yeah, but I think because they're in the early modern period when calculus was starting to really show its power. So in probability, in differential equations, in analysis, the Bernoullis are, you often see results with Bernoulli. Algebra, especially modern algebra, is a modern discipline, right? So chances are you're more likely to see people from in the names of people from late 19th century, early 20th century, even the 21st century, So yeah, so I was talking about the geometric interpretation of Bernoulli's inequality. The function f should have a graph that looks like this. And let's calculate f prime. F prime of alpha, just use the power rule and the chain rule, you get n times 1 plus alpha raised to the n minus 1. And evaluate that at 0, you get f prime of 0 is n. So the slope at x equals 0, alpha equals 0 is n. And of course, the function f of alpha equals 1 when alpha equals 0. So that means the tangent line the tangent line use the slope and intercept form is just 1 plus alpha n. The intercept is 1, slope is n. And because of the function f of alpha is convex, it lies above all of its tangent lines, and this is just a particular instance of it. So that's the geometric interpretation of the Bernoulli's inequality. And of course, here we're not assuming calculus. We're going to prove this in a more elementary way. Okay, it's okay if we don't actually finish proving this because I have to leave in 10 minutes. Let's just finish proving the Bernoulli's inequality. And this is an excellent exercise in induction because this is a statement that's true for all n in the set of natural numbers. So let's do induction. So JC also published videos on inductions as well. So go check out his, it's in the playlist Math Can Be a Hobby, Introduction to Pure Math Theories. So induction, and he has a very funny way of explaining it, a Luna knocking over math books. You know, induction is typically introduced as an analogy of falling dominoes, right? And we often see his cat on the live stream, and I guess that was the inspiration. Anyway, so coming back to proving the Bernoulli's inequality, let's just start by checking the base case. Okay, so let's say we prove the inequality using an induction on n. Okay, so let's start with the base case, n equals 1. So when n equals 1, of course, the result is trivial. So 1 plus alpha raised to the 1 is, of course, greater or equal to 1 plus alpha. So we're done, which is true. Actually, you know what? We will add another sentence just to conform with our usual strategy for writing proofs. There's a for all alpha greater than -1, so let alpha greater than -1. Okay, and then let alpha greater than -1, so this is now considered a fixed number. Okay, and now let's do the inductive step. The inductive step starts by assuming the induction hypothesis. So we can say assume the inequality is true for some n. Assume the inequality is true for some n. So that is to say 1 plus alpha raised to the n greater or equal to 1 plus n alpha. Okay, so for beginners in induction, this might look a little bit confusing. Isn't this what we're trying to prove? Here we're assuming it. What is going on? Well, the crucial distinction lies in the quantifier. The conclusion that we wish to prove says for all n, the inequality is true. Here we're only assuming this is true for some n. So that's not assuming the conclusion. Okay, and sometimes to make it extra clear, you can also say for some k, just as a notational helper, so to say, to remind ourselves that this is not assuming the conclusion. Instead of using n, you write k as a different letter. I'm not going to bother doing that, but it's sometimes helpful. Okay, sometimes it can be helpful just to tell the induction hypothesis apart from the actual conclusion. This is the induction hypothesis. Okay, because simply looking at the inequality, they might look exactly the same, but due to the difference in quantifiers, they are really different statements. So assuming the induction hypothesis, we need to show the inequality is true for n plus 1. Need to show 1 plus alpha to the n plus 1 is greater or equal to 1 plus n plus 1 times alpha. There you go. So here we go. We have, at some point in the deduction, we have to use induction hypothesis. So this is another very common, so to say, mistake in analysis or in induction proof, is that you assume the induction hypothesis, everyone knows that, but somehow in the proof, the application of the induction hypothesis is absent. Then that's a great indication that the proof is wrong. Okay, the inductive step must use the induction hypothesis. Otherwise, there's a great chance that the proof is false. Okay, so to make use of this inequality, it's natural to break the n's power, n plus 1's power, into 1 plus alpha to the n times 1 plus alpha. And now that you have a 1 plus alpha to the n, and because this is important, and because alpha is greater than minus 1, this way 1 plus alpha is positive. Otherwise, if this is negative, then this screwed up the inequality sign. Right, so you want to use 1 plus alpha to the n is greater or equal to 1 plus n alpha. And because 1 plus alpha is a positive number, so the inequality direction is preserved. Okay. So even though, based on the diagram here, this is also true for alpha less than minus 1. This is also true. Look at the picture. The graph of 1 plus alpha is above the support line or the tangent line everywhere for all alpha. Even for alpha less than 1, this is also true. Oh, actually no. Actually, guys, no, that's not true, because here I'm only assuming n is even. When n is even, then this is a globally convex function. If n is odd, then you have this shape going on. It's like if it's a cubic function, then less than, if n is odd, you can go, the function can go this way when alpha is less than minus 1, in which case it will eventually fall under the support line. Okay, so even though this diagram is useful, it's actually misleading for certain values of it. So be very careful, actually. So it's not true for all the alpha. It's not true for all the alpha, okay? If you say n can be arbitrary, this is only true for n greater than minus 1. So be careful about that. All right, so here we have this inequality using the induction hypothesis. So actually, to emphasize that, we can put an IH on top of this inequality to emphasize here. This is the exact position where we use the induction hypothesis. So it's helpful for the reader, and it's helpful for us to check. Okay, so this is the step where we use the induction hypothesis, and then you just expand this new product, and I think that should be it. So expand this new product, you get 1 plus n plus 1 quantity times alpha plus n alpha squared. And of course, n alpha squared is non-negative. Therefore, this is greater or equal to 1 plus n plus 1 quantity times alpha as needed. Okay, I always write things like as needed when there's a need to show something at the front, just to kind of close the bracket. It's like, if I say claim something and I finish the proof of claim, I write as claim, as claimed. So it's also a nice way to create structure in the proof. All right. So yeah, that's it, right? So you have proved the inductive step, and to finish up the argument, you can finish up the proof. You can say, therefore, by the principle of mathematical induction, which is a theorem, by the principle of mathematical induction, the inequality is true for all n. Oh, hi, hi guys. Is that a Christian? K which, is that Christian? If so, hi Christian. Principle of mathematical induction. Oh, hi Steve. Thank you very much for your generosity and for joining the stream. Thank you guys. So by the principle of mathematical induction, we say for all n, but unfortunately I have to leave very soon. Okay, I have to leave very soon. So this is already 9. For all n, and this evening I'll have a stream on transform stuff, Laplace transform, Fourier transform, explain where they come from, why they're useful, things like that. Okay, so hopefully we'll see you guys there. Okay, so that'll be it. Okay, so this is our lemma for proving the limit, and the compound interest limit exists. Okay, which we will continue. Actually, maybe not tomorrow, but next week. Tomorrow I have other plans. Okay, awesome. That will be it. Thank you very much, guys, for joining the stream. And I will see you in a few hours. Later tonight. So 6:30. So it's 9.5 hours from now. We'll do a stream on the transform stuff. Fourier transform, Laplace transform. Which is an awesome topic. I can't believe I've been running an applied math channel for 2 years without touching Fourier transform. This is criminal. Okay. Anyway, guys, see you. Bye.